Welcome to Softly Curious. Gravity is so constant that it almost becomes invisible. It does not flicker or surge. It does not rest. It holds oceans against the earth, guides rain toward the soil, and keeps the moon from drifting into the dark. Long before it was described with symbols, it shaped every falling stone and every rising tide. In the ancient world, gravity was not yet understood as a force. Aristotle described motion as a search for natural place. Earth and water, being heavy, moved downward toward the center of the world. Air and fire, lighter by nature, moved upward. A stone did not fall because it was pulled. It fell because the ground was where it belonged. Rest was considered the natural state of heavy matter. Motion required a reason. From this idea grew a quiet certainty that heavier objects fall faster than lighter ones. The logic felt intuitive. A large rock appears more forceful than a feather. Without instruments to measure time precisely, the difference in air resistance between dense and light materials made the belief convincing. For centuries, this assumption stood largely unchallenged. During the Middle Ages, scholars began to refine these ideas without abandoning them entirely. The concept of impetus emerged as a way to explain why objects continued moving after being thrown. Instead of motion ending the moment contact ceased, it was suggested that an internal quality was impressed upon the object. Jean Buridan proposed that this impetus depended on speed and mass, and that it diminished gradually due to resistance. It was not yet inertia in the modern sense, but it moved thinking forward. Motion no longer required continuous pushing. Something persisted within the object itself. Careful observation began to replace inherited certainty. In the late 16th century, Galileo Galilei turned attention from philosophy to measurement. Rather than dropping objects from towers in dramatic demonstrations, he used inclined planes to slow motion down. By rolling spheres along gentle slopes, he could measure time with water clocks and count beats with steady rhythm. Slowing gravity revealed its pattern. Through these experiments, a quiet symmetry appeared. Objects of different masses accelerated at the same rate when air resistance was minimized. The difference between a heavy ball and a lighter one was not in their falling speed, but in the force required to change their motion. The acceleration of free fall near Earth's surface remained constant. Weight did not determine how quickly something sped up as it descended. Vacuum experiments later strengthened this realization. When air was removed, objects that once seemed to fall differently reached the ground together. The resistance of air, not gravity itself, created the illusion of unequal speeds. A feather and a coin behave differently in air, but in a vacuum, their descent aligns. Gravity acts equally on mass. It does not prefer density or size. At the same time, the sky was being observed with increasing precision. The motion of the moon presented a subtle puzzle. It did not drift away into space, nor did it crash to Earth. One emerging intuition suggested that perhaps it was falling continuously, but missing the ground because of its sideways motion. The idea that orbit might be a form of perpetual fall began to take shape, though it lacked the mathematical clarity to be fully expressed. The work of Johannes Kepler provided the first precise description of planetary motion. Studying the careful observations of Tycho Brahe, he discovered that planets do not move in perfect circles. Their paths are ellipses, with the sun at one focus. This simple shift from circle to ellipse altered astronomy profoundly. The heavens were not governed by geometric perfection, but by measurable law. Kepler's three laws described how planetary speed changes along the orbit, moving faster when closer to the sun and slower when farther away. The pattern hinted at an invisible influence that weakened with distance. The next great step unified falling apples and orbiting planets under one principle. Isaac Newton proposed that every mass attracts every other mass. The strength of this attraction depends on the product of their masses and decreases with the square of the distance between them. This inverse square relationship means that if the distance doubles, the force becomes 4 times weaker. If the distance triples, the force becomes 9 times weaker. The law applied equally to stones, moons, and planets. With this formulation, gravity became universal. The same principle that pulls a book toward the floor also holds Jupiter in its orbit. There was no longer a separation between terrestrial and celestial physics. Earth and sky obeyed the same equation. Newton's model also implied something striking. Gravity acts across empty space. It requires no visible medium. The force appears to operate instantly, regardless of distance. This assumption of instantaneous action was accepted because it worked mathematically. Predictions matched observation with remarkable precision. The publication of Philosophiae Naturalis Principia Mathematica in 1687 marked a turning point. The work was dense, geometric, and exacting. It provided not just a description of motion, but a framework capable of predicting future positions of celestial bodies. Gravity was no longer an observed tendency. It was a calculable interaction. One early triumph involved the path of a comet. Edmund Halley examined historical sightings of comets and noticed similarities in their trajectories. Using Newton's equations, he calculated that the comet observed in 1682 would return after approximately 76 years. Its reappearance in 1758 confirmed the predictive strength of universal gravitation. A wandering object in the sky became a scheduled visitor. Gravity also explained the tides. The rise and fall of ocean waters follow a rhythm linked to the positions of the moon and the sun. The gravitational pull on Earth's oceans creates 2 bulges, one facing the moon and one on the opposite side. As Earth rotates, coastlines pass through these bulges, producing regular high and low tides. The mathematics accounted for subtle variations, including spring tides when sun and moon align, and neap tides when their poles partially offset each other. Through these developments, gravity transformed from philosophical intuition to quantitative law. It described falling bodies, planetary paths, comet returns, and ocean rhythms within a single structure. Its reach extended from a dropped pebble to the outer planets. And yet, within its strength, there were quiet questions. The mechanism of attraction across empty space remained unexplained. The assumption of instantaneous influence was mathematically convenient, but conceptually unsettled. The equations worked with extraordinary accuracy, but they described what gravity does, not how it truly operates. By the end of this classical era, gravity stood as one of the most successful ideas in science. It unified heaven and earth under a shared principle and allowed humanity to predict the future positions of distant worlds. It felt complete, balanced, and powerful. But completeness in science is often temporary. Beneath its precision, small tensions waited patiently, almost invisible, like fine cracks in polished stone. If gravity could be written into an equation, the next question was quieter but heavier. How strong is it, exactly? Not in theory, but in number. The force that binds oceans and moons is surprisingly weak when tested between small objects. Measuring it required patience more than brilliance. In the late 18th century, Henry Cavendish built an apparatus delicate enough to feel the faint pull between lead spheres. His torsion balance used a thin wire that twisted under gravitational attraction. When large masses were positioned nearby, the smaller suspended spheres shifted almost imperceptibly. The angle of twist revealed the force. The motion was slight, but measurable. From this experiment came the first value of the universal gravitational constant, known as g. This constant sets the scale of gravity's strength in the equation describing attraction between masses. It is extraordinarily small. That smallness explains why gravity dominates only when masses are immense. Between everyday objects, it is almost silent. With g measured, the mass of the Earth could be calculated. By observing the acceleration of falling bodies at the surface, and combining it with the gravitational constant, scientists determined how much matter our planet contains. The Earth's mass was no longer a philosophical abstraction. It became a number, expressed in kilograms, precise and finite. As measurements improved, it became clear that gravitational acceleration is not identical everywhere. The value near the equator differs slightly from the value near the poles. This variation arises partly because Earth rotates. Rotation creates a centrifugal effect that slightly counteracts gravity at lower latitudes. The difference is small, but detectable. Another factor shapes this variation. Earth is not a perfect sphere. It bulges at the equator due to its rotation, creating what is known as equatorial flattening. The distance from the center of the Earth to the surface is greater at the equator than at the poles. Because gravitational force weakens with distance, this shape contributes to measurable changes in acceleration. Beyond these predictable differences lie gravitational anomalies. In some regions, gravity is slightly stronger or weaker than expected. These deviations reflect variations in subsurface density. Dense rock formations exert a marginally stronger pull. Cavities or lighter materials reduce it. Gravity becomes a map of hidden structure. To detect such subtle changes, gravimeters were developed. These instruments measure tiny differences in gravitational acceleration, often using springs, superconducting systems, or atomic interferometry. Modern gravimeters can detect variations as small as a few microgals, a unit equal to 1/1,000,000th of a gal, where 1 gal represents 1 centimeter per second squared. These measurements found practical application in mineral exploration. Because dense ore bodies alter local gravity slightly, survey teams can infer underground deposits without excavation. Gravity surveys help identify iron formations, salt domes, and other geological features. What cannot be seen can still be weighed indirectly. At larger scales, gravitational data has been used to understand the topography of the ocean floor. Even beneath kilometers of water, mass distributions influence the gravitational field. Satellites detect subtle differences in sea surface height caused by underwater mountains and trenches. The ocean's surface mirrors the invisible contours below, rising slightly above denser regions. Precision in measurement has often advanced through the pursuit of optical stability. Albert A. Michelson contributed to techniques of extreme accuracy, refining interferometry to measure distances and physical constants with remarkable sensitivity. Such work indirectly strengthened gravitational research by improving the tools used to calibrate instruments and detect minute variations. In the 21st century, space-based measurements extended this effort further. The GRACE mission, consisting of twin satellites orbiting Earth in tandem, measured changes in gravitational pull by tracking the distance between them. As the leading satellite passed over a region of greater mass, it accelerated slightly, altering the separation. These shifts, recorded with micrometer precision, revealed how mass moves across the planet. Through these observations, scientists have tracked the melting of polar ice sheets. When glaciers lose mass, the local gravitational field weakens slightly. GRACE data has shown measurable reductions in gravity over Greenland and Antarctica, reflecting the redistribution of water into the oceans. Gravity becomes a record of climate change, written in numbers rather than images. Even large infrastructure projects leave faint gravitational signatures. When massive reservoirs fill behind dams, the added water increases local mass. Sensitive instruments detect these changes. Gravity responds not only to mountains and oceans, but to human engineering. And yet, as precision increases, so do the subtleties. Tiny discrepancies sometimes appear between prediction and observation. Small residual differences persist after accounting for rotation, shape, and density. They are not dramatic. They do not overturn established laws. But they suggest that even a force we can measure with extraordinary care may still contain layers not yet fully resolved. By the early 20th century, Gravity was precise, predictive, and deeply trusted. It described falling bodies and planetary motion with remarkable accuracy. Yet small tensions remained. Certain motions did not align perfectly with calculation. Light, according to classical theory, should not be influenced by gravity at all. And the assumption that gravitational influence traveled instantly across space rested more on convenience than explanation. In 1915, Albert Einstein introduced a different framework. Gravity, in his view, was not a force transmitted between masses. It was a property of geometry. Mass and energy reshape the structure of the universe itself. Instead of pulling objects across empty space, gravity curves the space through which objects move. This shift required a new concept: spacetime. Space and time were no longer separate backgrounds. They formed a single four-dimensional structure in which events occur. Position and duration were interwoven. A change in mass did not simply alter spatial relationships. It altered the geometry of spacetime. Objects followed the natural paths within that geometry. One of the central insights supporting this idea was the equivalence principle. It states that gravitational acceleration and acceleration due to motion are locally indistinguishable. A person inside a closed elevator cannot tell whether the force pressing them to the floor comes from gravity or from the elevator accelerating upward. In a small enough region, the effects are identical. Gravity and acceleration share the same behavior. This principle explains why weight disappears in free fall. When an object falls freely, it is not resisting gravity. It is following the natural curvature of spacetime. Inside a falling elevator, occupants would feel weightless because both they and the elevator accelerate together. Weight arises only when motion is prevented, when the ground pushes upward against the body. General relativity, as Einstein's theory became known, described gravity not as attraction, but as curvature. A massive body like the Sun creates a distortion in spacetime. Planets move along the curved paths shaped by that distortion. Their orbits are not maintained by a pulling force, but by geometry. Motion follows the contours of a curved landscape, though the landscape itself is invisible. One of the first tests of this theory concerned Mercury. The planet's orbit shifts slightly over time, a motion known as perihelion precession, meaning the gradual rotation of the point where it comes closest to the Sun. Classical predictions accounted for most of this shift, but a small excess remained unexplained. General relativity provided the missing correction. The curvature of spacetime near the Sun accounted precisely for the discrepancy. Another prediction followed naturally. Light should bend near massive objects. Although light has no rest mass, it follows the curvature of spacetime. When starlight passes close to the Sun, its path shifts slightly. This effect is small but measurable. In 1919, during a solar eclipse, Arthur Eddington led an expedition to measure this deflection. With the Sun temporarily obscured, stars near its edge became visible. Photographs taken during the eclipse were compared with reference images. The observed shift in starlight matched the prediction of general relativity. The result brought global attention to Einstein's work. Gravity, it seemed, could bend even light. General relativity also predicts that time itself is affected by gravity. Clocks positioned in stronger gravitational fields tick more slowly than those farther away. This phenomenon, known as gravitational time dilation, means that time passes at slightly different rates depending on location. Near Earth's surface, the effect is small but measurable with precise instruments. Far from massive bodies, time advances more quickly. The mathematics describing this curvature is complex. Soon after Einstein published his equations, Carl Schwarzschild found an exact solution for the gravitational field outside a spherical mass. His solution revealed that if an object is compressed within a certain radius, space-time curvature becomes extreme. This critical boundary is now known as the Schwarzschild radius. At that radius lies what is called an event horizon. It marks a boundary beyond which no signal can return. The curvature of spacetime becomes so strong that all paths lead inward. From outside, the horizon appears as a surface from which light cannot escape. The concept emerged directly from the geometry of the equations. General relativity also predicts gravitational redshift. Light climbing out of a gravitational well loses energy, and its wavelength stretches toward the red end of the spectrum. This shift does not arise from motion, but from the influence of gravity on time and energy. Photons emitted near massive bodies arrive slightly altered when observed from afar. Each of these predictions expanded the meaning of gravity. It was no longer simply a force connecting masses. It shaped distance, altered time, redirected light, and defined horizons. The universe was not a stage on which gravity acted. The stage itself responded. What is striking is that these effects are often subtle. The bending of light near the sun amounts to a fraction of a degree. The difference in clock rates near Earth's surface is measured in tiny fractions of a second. Yet these small variations accumulate. They reveal that gravity is woven into the structure of reality. The theory replaced the idea of instantaneous action with a finite structure. Changes in mass influence spacetime in a way that propagates at a defined speed. Geometry responds, and objects respond to geometry. The picture is quieter but deeper. Instead of invisible strings pulling across emptiness, there is curvature guiding motion. At everyday scales, classical predictions remain extremely accurate. For falling objects in planetary paths, the differences are minimal. But near massive bodies or over long periods, the curvature becomes measurable. Subtle discrepancies that once lingered unresolved found explanation within this framework. Gravity, in this view, is not an added ingredient to the universe. It is a property of its shape. Mass tells spacetime how to curve. Curved spacetime tells matter how to move. The relationship is continuous and reciprocal. This understanding opened a door to regions where curvature grows stronger, where geometry tightens and paths narrow. In such places, gravity does not simply guide motion. It dominates structure itself. And it is there, in the presence of extreme mass and density, that the consequences of curved spacetime become most dramatic. When mass gathers beyond ordinary limits, gravity no longer feels gentle or geometric. It becomes decisive. In certain regions of the universe, matter collapses so completely that familiar structure gives way to extremes. Black holes are not rare accidents, but natural outcomes of stellar evolution. When massive stars exhaust their nuclear fuel, their cores can collapse inward under their own gravity. If the remaining mass exceeds a critical threshold, no known force can halt the contraction. The result is a region where escape becomes impossible. For decades, black holes were inferred indirectly. Their presence was deduced from the motion of nearby stars or from intense radiation emitted by infalling matter. But the most dramatic confirmation came through gravitational waves, ripples in spacetime produced by accelerating massive objects. In 2015, the observatory known as LIGO detected such a signal for the first time. Two black holes, orbiting each other at high speed, spiraled inward and merged. The collision released energy in the form of gravitational waves that traveled across the cosmos for more than 1 billion years before gently stretching and compressing the detectors on Earth by less than the width of a proton. These waves are not sound traveling through air. They are oscillations in the fabric of spacetime itself. As they pass, distances expand and contract in alternating patterns. The signal recorded by LIGO matched precisely the predictions for merging black holes. It was not light that carried the message, but motion encoded in geometry. Extreme gravity also produces neutron stars. When a star collapses but remains below the mass required to form a black hole, its core compresses into an object only about 20 kilometers across. The density becomes so high that protons and electrons combine into neutrons. A teaspoon of neutron star material would weigh billions of tons on Earth. Within such stars, matter approaches nuclear density, meaning density comparable to that inside atomic nuclei. At these levels, the familiar distinction between individual particles blurs. The star becomes a single, tightly packed structure, held together by gravity, balanced against quantum pressure. If one were to approach a black hole too closely, tidal forces would stretch the body dramatically. This process is sometimes described as spaghettification. The gravitational pull on the feet would exceed the pull on the head, elongating the body along the direction of fall. The difference in force arises from steep gradients in gravity near extremely compact objects. In 2019, the Event Horizon Telescope released the first direct image of a black hole's shadow. By linking radio telescopes across the globe, it achieved resolution sufficient to observe the silhouette of a supermassive black hole against glowing surrounding gas. The image revealed a dark central region bordered by a ring of light shaped by intense gravitational effects. That black hole resides at the center of the galaxy M87. Closer to home lies Sagittarius A*, the supermassive black hole at the center of our own Milky Way. Observations of stars orbiting this region show rapid motion around an unseen mass millions of times greater than the Sun. The orbits provide strong evidence for a compact, gravitational source at the galactic core. Mathematically, the inevitability of such collapsed regions was explored through singularity theorems developed by Roger Penrose. These theorems demonstrate that under general conditions, gravitational collapse leads to points where curvature becomes infinite, meaning the equations predict a breakdown of known physics. The singularity marks a boundary of current understanding. Another surprising insight came from Stephen Hawking, who proposed that black holes are not entirely black. Quantum effects near the event horizon allow for the emission of what is now called Hawking radiation. This radiation implies that black holes can slowly lose mass over immense timescales. The concept connects gravity with quantum theory in subtle ways. In merging black holes and dense neutron stars, gravity shapes events that release enormous energy without producing visible light. In the stretched signals recorded by detectors, and in the faint radio images constructed from global networks, gravity reveals itself not as a background condition, but as an active participant in cosmic evolution. These extreme environments are distant, yet their study relies on instruments built by human hands, calibrated to extraordinary precision. Vibrations measured in fractions of atomic width, radio waves captured across continents, equations traced across chalkboards all converge on understanding these distant masses. From the compression of neutron matter to the merging of black holes, gravity reveals its most concentrated expressions. In those distant regions, it sculpts stars into remnants only kilometers wide and drives collisions that ripple across galaxies. The magnitudes are immense, the energies difficult to imagine, yet the governing principle does not change. What varies is scale, not nature. The same structure that allows spacetime to fold inward around collapsed stars also shapes the steady curvature that keeps planets in orbit. There is no separate version of gravity reserved for extremes. There is only one framework, expressed gently here and intensely elsewhere. When we step away from telescopes and return to familiar ground, gravity does not become less profound, it becomes quieter. It defines vertical and horizontal, up and down. It determines how tall mountains can rise before their own weight limits them. It sets the rhythm of falling rain and the arc of every thrown object. In this way, the universe does not divide into distant drama and ordinary life. The curvature that governs remote stellar remnants continues seamlessly into the forces that shape our posture and movement. The difference lies only in degree. Gravity remains constant, whether guiding galaxies or resting beneath our feet. Gravity is not only something we observe outside the body. It is something the body quietly expects. From the density of our bones to the balance of our inner ear, human physiology developed under a constant downward pull. Remove that pull, and subtle systems begin to shift. Bone is not inert material. It is living tissue, continuously remodeled through a balance of formation and resorption. In the 19th century, Julius Wolff observed that bone structure adapts to the loads placed upon it. This principle, now known as Wolff's law, states that bone grows stronger in response to stress and weakens when stress is reduced. Weight bearing is not incidental. It is instructional. The internal architecture of bone reflects this adaptation. Trabecular bone, the spongy lattice found at the ends of long bones and within vertebrae, aligns along lines of mechanical stress. These microscopic struts distribute force efficiently. Under Earth's gravity, walking, standing, and even sitting apply regular pressure that signals bone cells to maintain density. Without load, that signal diminishes. Gravity also shapes our sense of orientation. The vestibular system, located within the inner ear, detects motion and position. It consists of semicircular canals that respond to rotational movement and otolith organs that respond to linear acceleration. Together, they provide a continuous estimate of where the head is in space. Within the otolith organs lie tiny calcium carbonate crystals, known as otoconia. These crystals rest on a gelatinous membrane covering hair cells. When the head tilts or accelerates, gravity causes the crystals to shift slightly, bending the hair cells beneath. This mechanical change converts physical movement into electrical signals sent to the brain. The sensation of down is not philosophical. It is cellular. Balance depends on integrating vestibular signals with vision and proprioception, the body's awareness of limb position. When gravity acts consistently, these systems calibrate against it. Sudden changes in acceleration, such as during a fall or a rapid turn, trigger reflexive adjustments. Muscles respond within milliseconds to prevent collapse. Circulation, too, is organized around gravity. Blood is a fluid subject to hydrostatic pressure, meaning pressure exerted by a fluid at rest due to gravity. When standing upright, blood tends to pool in the lower extremities. To compensate, veins contain one-way valves that prevent backflow. Skeletal muscle contractions help push blood upward toward the heart. Arterial pressure must overcome gravity to deliver blood to the brain. Baroreceptors, specialized pressure sensors in blood vessel walls, monitor changes and adjust heart rate and vessel diameter accordingly. A sudden shift from lying down to standing can briefly reduce blood flow to the head, producing lightheadedness. The body corrects this quickly, but the adjustment reflects gravity's constant influence. Muscle tone, the low-level contraction present even at rest, is partly maintained to resist collapse under gravity. Postural muscles in the back, neck, and legs remain subtly active while standing. These muscles do not wait for movement. They anticipate downward force. Without this background activity, upright posture would not be possible. Reflexes associated with falling illustrate how deeply gravity is embedded in neural circuits. When the body senses rapid downward acceleration, protective responses activate. Arms extend, muscles contract, and balance strategies engage. These reflexes are automatic and rapid, shaped by repeated exposure to gravitational forces throughout development. Learning to walk reveals gravity's role in motor development. Infants initially lack coordinated control over posture. They experiment with balance through small shifts in weight. Falling is common. Over time, the nervous system refines its predictions. Muscles activate in precise sequences to counteract gravity's pull while allowing forward motion. During early steps, children adopt a wide stance, increasing their base of support. This reduces the torque, or rotational force, that gravity can create around the ankles. As coordination improves, stance narrows and movement becomes more efficient. Walking becomes less an act of resisting gravity and more a negotiation with it. Even subtle aspects of body structure reflect downward adaptation. The curvature of the spine distributes compressive forces. The arches of the feet absorb impact. Joint surfaces align to manage load during standing and locomotion. These anatomical features are not decorative. They are responses to continuous vertical stress. Gravity also influences breathing. The diaphragm moves downward during inhalation, expanding the lungs. In upright posture, gravity affects how air distributes within lung tissue. Lower regions receive slightly more blood flow due to hydrostatic effects. Ventilation and perfusion align, partly because of vertical orientation. Sleep positions change gravitational relationships within the body. Lying down redistributes blood volume more evenly. The heart no longer works against a strong vertical column of fluid. Swelling in the legs often decreases overnight. The shift in pressure demonstrates how even rest is organized by gravity. Over time, the body maintains equilibrium through constant adjustment. Bone cells remodel in response to load. Muscles adapt to habitual posture. Neural pathways refine balance strategies. None of this requires conscious attention. Gravity acts continuously, and the body responds continuously. The downward pull is not experienced as force most of the time. It is experienced as normal. Only when balance falters, when dizziness occurs, or when a fall interrupts expectation, does gravity become noticeable. Its constancy allows it to disappear into the background of perception. Human physiology, from microscopic crystals in the inner ear to the dense columns of bone in the legs, reflects life under a stable gravitational field. Remove that field, and the system begins to recalibrate. The body that seems independent of its environment is, in fact, quietly shaped by it. We are built not simply to exist in gravity, but to rely on it. It guides growth, supports circulation, organizes posture, and trains movement from the first unsteady step onward. Downward is not just a direction. It is a condition written into the body's design. When gravity is reduced, the body does not simply feel lighter. It begins to renegotiate its internal rules. Systems that evolved under constant downward pressure encounter a new condition, near weightlessness. In orbit, this change is not the absence of gravity, but continuous free fall, creating the experience of floating. Aboard the International Space Station, astronauts circle Earth at roughly 28,000 kilometers per hour. They are not beyond gravity's reach. Instead, they are perpetually falling around the planet. This orbital motion produces microgravity, a state in which objects appear weightless because everything accelerates together. In this environment, the skeletal system receives far less mechanical loading. Without the constant compression produced by standing and walking, bone remodeling shifts. Osteoclast activity, meaning the process by which bone is broken down, begins to outpace bone formation. Astronauts can lose approximately 1 to 2% of bone density per month in weight-bearing regions such as the hips and spine. This loss resembles osteoporosis on Earth, though it occurs more rapidly. The absence of vertical stress reduces the signal that normally maintains trabecular structure. Even with structured exercise programs using resistance machines designed for space, some reduction persists. Recovery after return to Earth can take months, and full restoration is not always guaranteed. Muscle tissue also adapts to reduced demand. Postural muscles that normally counteract gravity experience less continuous activation. Over time, muscle fibers shrink in a process known as atrophy. Strength declines, particularly in the legs and lower back. Astronauts must follow strict daily exercise regimens to mitigate these effects. Microgravity alters fluid distribution as well. On Earth, gravity pulls fluids toward the lower body. In orbit, this gradient disappears. Blood and interstitial fluids shift toward the head and chest. Astronauts often describe a sensation of facial fullness during the first days in space. The body responds by reducing overall plasma volume, adjusting to what it perceives as fluid excess. This upward fluid shift can influence vision. Some astronauts experience changes collectively referred to as spaceflight-associated neuroocular syndrome. The altered pressure dynamics may affect the shape of the eye and the optic nerve. Vision can become slightly blurred. Researchers continue to investigate the precise mechanisms behind these changes. Balance systems also adapt. Without a consistent downward cue, the vestibular system recalibrates. Early in a mission, astronauts may feel disoriented as the inner ear's expectations conflict with visual input. Over time, the brain reinterprets signals, learning to operate without a dominant gravitational reference. Even the heart adjusts. In microgravity, it does not need to pump against a vertical column of blood. Cardiac muscle mass can decrease slightly due to reduced workload. Upon return to Earth, some astronauts experience temporary difficulty maintaining blood pressure while standing, as the cardiovascular system readapts to hydrostatic stress. To counteract these effects, the concept of artificial gravity has long been considered. One proposed method involves rotation. When a structure spins, centrifugal acceleration pushes objects outward, simulating the sensation of weight along the outer rim. The faster the rotation or the larger the radius, the stronger the perceived gravity. Rotating habitat designs explore this principle. Cylindrical or ring-shaped stations could create a gradient of artificial gravity from center to edge. Inside such a structure, floors would align with the outer wall, and occupants would feel a steady outward pull. Engineering challenges remain significant, including structural stress and motion sickness due to rotation. Short radius centrifuges have also been studied for intermittent use. Astronauts could spend limited periods under simulated gravity to stimulate bones and muscles. Whether partial daily exposure would sufficiently preserve physiological systems is still under investigation. Future missions to Mars introduce additional complexity. Martian gravity is approximately 38% of Earth's. This partial gravity may reduce some effects of microgravity, but may not fully prevent bone and muscle loss. Long-duration habitation on Mars would provide valuable data about how the human body adapts to intermediate gravitational environments. Ground-based simulations attempt to approximate aspects of weightlessness. Bed rest studies, in which participants remain in a head-down tilt position for extended periods, mimic certain fluid shifts and musculoskeletal unloading. These experiments reveal how quickly the body begins to change when normal gravitational stress is reduced. Over time, adaptation to microgravity becomes more efficient. Astronauts float with ease, orient themselves in 3 dimensions, and perform complex tasks without a defined up or down. The nervous system reorganizes its spatial framework. Movement becomes economical within the new environment. Yet adaptation does not erase dependency. The body does not become neutral to gravity. It becomes temporarily tuned to a different condition. Upon returning to Earth, many astronauts describe the renewed sensation of weight as surprising. Muscles strain against familiar forces. Balance requires renewed calibration. These changes reveal how deeply gravity is integrated into physiology. Bone density, muscle tone, fluid distribution, and sensory orientation are not fixed traits. They are ongoing negotiations with environment. Remove gravity's steady signal, and the body responds with measurable transformation. Life without weight is not an absence of structure. It is a different structure, one that exposes the assumptions built into biology. Microgravity highlights what normally goes unnoticed, that our bodies are engineered around a constant downward field. From orbiting laboratories to plans for rotating habitats and planetary settlements, the study of life in reduced gravity extends beyond curiosity. It informs long-term exploration and deepens understanding of human resilience. In observing how the body changes, we learn how precisely it has been shaped. Gravity, whether present as steady pressure or reduced to near absence, remains central. Its influence persists even when it seems to vanish. And as research continues, the quiet relationship between body and force becomes clearer, preparing us to understand not only distant worlds, but the ground we stand on each day. Before there were planets, there was dust. Not scattered randomly, but arranged within a rotating disk of gas and microscopic particles surrounding a young star. Gravity, even in its earliest role, was patient. It did not assemble worlds instantly. It gathered grains. These structures are known as accretion disks, meaning flattened rotating disks of material formed by gravitational attraction around a central mass. Within such a disk, particles orbit the newborn star while gradually colliding and sticking together. Static electricity and gentle impacts allow millimeter-sized grains to become pebbles, pebbles to become rocks, and rocks to become kilometer-scale bodies called planetesimals. As mass increases, gravity strengthens. Larger bodies begin to attract smaller ones more efficiently. Collisions become less about adhesion and more about accumulation. Over millions of years, repeated mergers produce protoplanets, objects massive enough to clear their orbital neighborhoods. The process is neither smooth nor orderly. Impacts are frequent. Some worlds are broken apart and reassembled. The distribution of material within the disk influences what forms where. Closer to the star, temperatures are high. Volatile substances such as water and methane evaporate, leaving behind heavier elements like iron and silicates. Farther out, cooler regions allow ices to condense. This temperature gradient helps explain why rocky planets tend to orbit near their stars, while gas giants form farther away, where abundant ices contribute additional mass. Gravity also defines boundaries. When a smaller body orbits a larger one too closely, tidal forces can exceed the smaller body's structural integrity. This threshold is called the Roche limit, the minimum distance within which a satellite held together only by gravity will begin to disintegrate due to differential gravitational pull. Inside this limit, tidal forces stretch and eventually fragment the object. Fragments produced near or within the Roche limit can form planetary rings. Rather than coalescing into a single moon, the material remains dispersed in orbit. Rings consist of countless particles, ranging from fine dust to large ice blocks, each following its own path, while collectively forming a thin, luminous band. The structure of rings is not static. Gravitational interactions with nearby moons create gaps and waves within the ring system. Resonances, meaning orbital relationships where periods align in simple ratios, can concentrate or disperse particles. The stability of rings depends on these ongoing interactions. In the 19th century, James Clerk Maxwell analyzed the dynamics of Saturn's rings and concluded that they could not be solid or fluid structures. Instead, they must consist of numerous independent particles orbiting the planet. His mathematical reasoning clarified that only a particulate system would remain stable over time. Observations later confirmed this conclusion. Gravity not only shapes formation, but also synchronizes motion. Tidal locking occurs when a satellite's rotation period matches its orbital period around a larger body. As a result, the same hemisphere always faces its primary. This synchronization arises because tidal forces gradually dissipate rotational energy, aligning spin with orbit. Earth's moon is tidally locked. One side perpetually faces Earth, while the far side remains hidden from direct view. This state is not instantaneous, but the outcome of billions of years of gravitational interaction. The repeated deformation of the moon under Earth's tidal pull converted rotational energy into heat, slowing its spin until equilibrium was reached. Tidal interaction works in both directions. While the moon is locked to Earth, Earth is not locked to the moon. Instead, the moon is gradually moving away from Earth at a rate of approximately 3.8 centimeters per year. This recession occurs because Earth's rotation transfers angular momentum to the moon's orbit through tidal friction in the oceans. Gravity reshapes motion subtly over long durations. The early Earth likely experienced stronger tides when the moon was closer. Geological evidence suggests that days were shorter in the distant past. As tidal friction slowed Earth's rotation, the length of a day increased. Gravity thus contributes not only to planetary structure, but to temporal rhythm. Beyond the inner rocky planets, gravity orchestrated the emergence of gas giants. In the colder outer regions of the disk, solid cores formed rapidly enough to capture large envelopes of hydrogen and helium before the disk dispersed. These massive planets exerted strong gravitational influence on surrounding debris. Jupiter, in particular, plays a protective role within the solar system. Its large mass alters the trajectories of comets and asteroids entering the inner regions. Some are deflected outward, others are captured or broken apart. While Jupiter does not eliminate all impact threats, its presence significantly reshapes the distribution of small bodies. At the same time, Jupiter's gravity has influenced the architecture of the asteroid belt. Resonances between Jupiter's orbit and that of smaller bodies create regions where stable orbits are impossible. These gaps, known as Kirkwood gaps, arise because repeated gravitational nudges destabilize material over time. The formation of planets is therefore not merely accumulation. It is selection, resonance, and redistribution. Gravity determines which bodies merge, which fragment, and which migrate. Orbital paths shift as massive planets interact with disks of debris, sometimes moving inward or outward from their original positions. Computer simulations of planetary formation reveal that migration can be significant. Gas giants may move closer to their stars before settling into stable orbits. Such movement influences the development of smaller planets, sometimes ejecting them or altering their paths. The solar system we observe today reflects a dynamic past shaped by gravitational negotiation. Even after formation stabilizes, gravity continues to govern structure. Planetary rotation flattens bodies slightly at the poles. Internal differentiation, meaning the separation of materials by density, occurs because gravity pulls heavier elements toward the core. Iron sinks, lighter silicates rise. Layers form within worlds. From dust grains in a disk to fully formed planets in stable orbits, gravity acts as architect and regulator. It gathers material, defines limits, synchronizes rotation, and sculpts ring systems. It determines how moons behave and how planets influence one another. The same principle that draws a falling object toward Earth also assembled Earth itself from scattered fragments orbiting a young star. Across millions of years, through collision and resonance, gravity shaped a system of ordered motion from diffuse beginnings. Worlds emerged not from design, but from steady accumulation under an invisible curve. Gravity does not stop shaping planets once they form. It continues to work internally, bending crusts, heating interiors, and altering orbits over immense spans of time. Some of the most active worlds in the solar system owe their energy not to sunlight, but to gravitational stress. Tidal heating occurs when a moon or planet experiences varying gravitational pull during its orbit. If the orbit is slightly elliptical, the distance between bodies changes over time. This variation causes repeated flexing of the smaller body's interior. Rock and ice deform under stress, and that deformation generates heat through friction. One of the most compelling examples lies beneath the icy surface of Europa, a moon of Jupiter. Although its exterior appears frozen and rigid, evidence suggests the presence of a subsurface ocean. The gravitational pull from Jupiter stretches Europa slightly during each orbit, creating internal heat that may keep water liquid beneath kilometers of ice. Surface features on Europa support this idea. Long fractures crisscross the ice, and regions appear to have shifted and refrozen. These patterns resemble drifting plates over a softer layer below. If a global ocean exists, it could contain more water than all of Earth's oceans combined, maintained not by proximity to the Sun, but by gravitational flexing. Another striking case is Enceladus, a small moon of Saturn. Despite its modest size, it emits plumes of water vapor and ice particles from fractures near its south pole. These geysers were observed by spacecraft and indicate ongoing internal activity. Tidal forces exerted by Saturn generate sufficient heat to sustain subsurface reservoirs of liquid water. The energy driving Enceladus plumes arises from orbital resonance with neighboring moons. This gravitational relationship keeps Enceladus' orbit slightly eccentric, preventing it from settling into a circular path. As long as the orbit remains elongated, tidal heating continues. Gravity thus sustains geological motion in a world that might otherwise be frozen solid. Beyond our solar system, gravity governs the architecture of exoplanet systems. Thousands of planets have been detected orbiting distant stars, many in configurations unlike our own. Some follow highly elongated paths. Others orbit extremely close to their stars, completing revolutions in just a few days. Hot Jupiter systems present one such configuration. These are gas giants comparable in mass to Jupiter, but orbiting much nearer to their stars. Their proximity subjects them to intense radiation and strong tidal forces. Many are tidally locked, meaning one hemisphere permanently faces the star while the other remains in darkness. The existence of hot Jupiters challenged early assumptions about planetary formation. According to standard models, gas giants should form farther from their stars. Their presence in close orbits suggests that migration occurred after formation. Gravitational interactions within the protoplanetary disk likely caused these massive planets to spiral inward. Orbital dynamics in compact systems can become intricate. Planets influence one another through gravitational resonance, stabilizing or destabilizing orbits over time. The timing of transits, when a planet passes in front of its star, often reveals the presence of additional planets through subtle variations. The star system known as TRAPPIST-1 contains 7 Earth-sized planets orbiting a small red dwarf star. Their orbits are tightly packed, with some completing revolutions in just a few Earth days. Several of these planets lie within the star's habitable zone, where temperatures could allow liquid water. Many of the TRAPPIST-1 planets are likely tidally locked to their star. In such cases, one side experiences perpetual daylight, while the other remains in continuous night. This configuration creates strong temperature gradients across the surface. Atmospheric circulation models suggest that winds could redistribute heat, potentially moderating extremes. Across icy moons and distant planetary systems, gravity does more than hold objects in orbit. It actively generates change. Through tidal heating, repeated stretching and flexing transform orbital energy into internal warmth. On Europa, this process likely sustains a subsurface ocean beneath an otherwise frozen crust. On Enceladus, similar gravitational stress powers jets of water vapor that escape into space, revealing liquid reservoirs below the surface. In both cases, energy does not come primarily from sunlight, but from orbital motion converted into heat. These interactions depend on subtle orbital eccentricities and resonances. When a moon's path is slightly elongated rather than perfectly circular, gravitational pull varies over the course of each orbit. That variation prevents internal equilibrium. Rock and ice deform rhythmically, generating frictional heating within. Resonant relationships with neighboring bodies help preserve this orbital shape, ensuring that the heating continues over geological time. Beyond our solar system, gravity shapes planetary systems with equal complexity. Exoplanets have been observed in tightly packed arrangements, in elongated orbits, and in configurations unlike our own. Hot Jupiter systems demonstrate how massive planets can migrate inward after formation, settling into close, short-period orbits around their stars. In the compact system known as TRAPPIST-1, multiple Earth-sized planets orbit in near-resonant chains. Their gravitational interactions stabilizing the architecture while likely locking several worlds into permanent day and night hemispheres. In each of these environments, gravity acts as both organizer and engine. It sculpts subsurface oceans beneath ice, drives geological activity, rearranges planetary positions, and determines rotational states. The same force that once gathered dust into worlds continues to influence their internal warmth and orbital rhythm. Long after formation ends, gravity remains present, quietly shaping the conditions under which planets evolve. Gravity feels most familiar in ordinary moments. It is present in rain, in the steady rhythm of a clock, in the quiet stability of buildings beneath a city. Its influence is so constant that it rarely demands attention, yet its effects shape the texture of daily life in precise and measurable ways. When rain begins to fall, each droplet accelerates toward the ground. At first, gravity increases its speed steadily. But as the droplet moves faster, air resistance grows. Atmospheric drag, meaning the frictional force exerted by air against a moving object, pushes upward against the descent. Eventually, the downward pull of gravity balances the upward drag. The droplet stops accelerating and continues falling at a constant speed. This constant speed is known as terminal velocity, the maximum velocity reached when gravitational force equals air resistance. For small raindrops, terminal velocity is relatively modest, often around a few meters per second. Larger drops fall faster, sometimes reaching speeds above 8 or 9 meters per second before air resistance stabilizes them. The size and shape of each droplet determine how quickly equilibrium is reached. Atmospheric resistance depends on several factors: air density, cross-sectional area, and the drag coefficient, which describes how streamlined an object is. A smooth, compact droplet experiences different resistance than a flattened or irregular one. As raindrops grow larger, surface tension struggles to maintain spherical shape. Some break apart before reaching the ground, limiting how large natural raindrops can become. Terminal velocity explains why falling objects behave differently depending on their interaction with air. A feather descends slowly because its broad surface area increases drag relative to its mass. A stone, more compact and dense, encounters proportionally less resistance and reaches higher speed. Gravity acts equally on both masses in terms of acceleration, but the atmosphere modifies the outcome. The same balance of force and resistance influences objects far beyond raindrops. Snowflakes, for example, fall slowly because their crystalline structures create high drag relative to weight. Hailstones, denser and smoother, descend more quickly. The interaction between gravity and air shapes the pace of precipitation and the experience of weather. Gravity also regulates timekeeping in traditional pendulum clocks. A pendulum swings back and forth under the influence of gravity, converting potential energy at the top of its arc into kinetic energy at the bottom. The period of a simple pendulum, meaning the time required for one complete swing, depends primarily on its length and the local gravitational acceleration. The formula for pendulum period includes the square root of the length divided by gravitational acceleration. This means that in regions where gravity is slightly weaker, a pendulum will swing more slowly. Early clockmakers had to account for small geographic variations. A clock calibrated at sea level could lose time at higher altitude, where gravitational acceleration is marginally reduced. The precision of pendulum clocks once defined standards of time. Their regular motion depended on gravity's consistency. Even small changes in local gravitational strength, whether due to altitude or underlying geology, could affect timing over long durations. Gravity provided both the driving force and the reference frame for mechanical time. In urban engineering, gravity plays a quieter but equally precise role. During subway construction, engineers sometimes measure subtle variations in gravitational acceleration to map underground density. Denser rock formations slightly increase local gravitational pull, while voids or softer materials reduce it. These measurements help identify stable ground for tunneling. Gravimetric surveys, meaning surveys that measure variations in gravity, can reveal hidden structures without excavation. By analyzing small changes in gravitational acceleration across a site, engineers infer the distribution of mass below the surface. In metro projects, such data reduces risk by identifying cavities, fault lines, or buried infrastructure. The differences measured are extremely small, often fractions of a microgauge, yet they carry meaningful information. Gravity does not fluctuate dramatically in daily life, but its minute variations reflect changes in density beneath our feet. Through careful instrumentation, these differences become readable patterns. Even in high-rise buildings, gravity's interaction with other forces must be considered. Structural design accounts for the constant downward load of materials, combined with lateral forces such as wind. The building's mass creates compressive stress on lower floors, while wind produces bending moments. Engineers calculate how these forces combine to maintain stability. Elevators, too, illustrate gravity's presence. When an elevator accelerates upward, passengers feel temporarily heavier because the floor exerts additional force. When descending rapidly, they may feel lighter. These sensations arise from the relationship between gravitational acceleration and the elevator's motion, echoing the equivalence between gravity and acceleration. Water systems in cities rely on gravity to maintain pressure. Elevated water towers create hydrostatic pressure by storing water above ground level. The higher the water column, the greater the pressure at ground level. Pumps assist, but gravity provides the baseline force that keeps water flowing through pipes. Even the arc of a thrown ball in a park follows predictable curvature. Its path, a parabola in simplified conditions, reflects constant downward acceleration combined with horizontal motion. Air resistance may slightly distort the trajectory, but gravity ensures the return to ground. In these ordinary contexts, gravity is not abstract geometry or distant cosmic force. It is the regulator of falling rain, the metronome of pendulums, the silent assistant in underground mapping. It sets limits on speed, shapes design constraints, and ensures continuity in motion. Daily life unfolds within a gravitational field that rarely varies enough to be noticed. Its stability allows predictable behavior, from precipitation to construction. Yet even within this apparent constancy, subtle variations can be measured and used. Gravity becomes not only a background condition, but a practical tool. The rain that falls, the clock that ticks, the tunnels that run beneath streets, all depend on a force that does not announce itself. It operates continuously, modest in appearance yet exact in effect. In the ordinary descent of a droplet or the steady swing of a pendulum, gravity expresses its precision without spectacle. Gravity continues to shape daily life in ways that are rarely visible, but constantly relied upon. One of the clearest examples lies in satellite navigation. The global positioning system depends on a constellation of satellites orbiting Earth, each carrying highly precise atomic clocks. These satellites broadcast time-stamped signals that receivers use to calculate position. For GPS to function accurately, timing must be exact to within billionths of a second. A discrepancy of even a few microseconds would translate into positioning errors of kilometers. Gravity affects these clocks. Because satellites orbit high above Earth, where gravitational influence is slightly weaker, their clocks tick faster than identical clocks on the ground. At the same time, the satellites move at high velocity relative to Earth's surface. Motion itself slows clocks slightly, according to relativistic principles. The gravitational and velocity effects do not cancel perfectly. Engineers must account for both. Without relativistic corrections applied to satellite timing, GPS accuracy would degrade rapidly. Orbit calculation is another domain shaped by gravity. Satellites remain in motion because their forward velocity balances Earth's gravitational pull. If they moved more slowly, they would descend. If they moved faster, they would escape. Orbital mechanics requires continuous adjustment, especially because Earth is not a perfect sphere. The planet's equatorial bulge, along with variations in mass distribution, causes small perturbations in satellite orbits. Gravitational anomalies influence trajectory over time. Ground stations monitor these deviations and update models to maintain stable positioning. Even slight shifts in altitude can affect signal timing and coverage. Space debris introduces additional complexity. Thousands of inactive satellites, rocket stages, and fragments orbit Earth. Each piece follows a path governed by gravity, but atmospheric drag at lower altitudes gradually slows some objects. As they lose speed, they descend and may re-enter the atmosphere. Collisions between debris objects can generate clouds of smaller fragments. This cascading effect, sometimes called the Kessler syndrome, refers to a scenario in which increasing debris leads to more collisions and more debris. Gravity keeps these fragments in orbit, but it also ensures that their paths intersect over time. Tracking debris requires careful modeling of gravitational forces combined with drag, solar radiation pressure, and interactions with Earth's magnetic field. Predicting conjunctions, meaning close approaches between objects, helps prevent operational satellites from being damaged. Small adjustments in velocity can alter orbital paths enough to avoid collision. Gravity also influences how high-rise buildings respond to environmental forces. A building's mass creates a constant downward load through its structure. Wind, however, applies lateral force. The combination produces oscillations that engineers must anticipate. The building must resist tipping moments while distributing gravitational load safely to its foundation. The taller the structure, the more significant the interaction between wind and gravity becomes. Wind can induce sway, especially at upper levels. Designers incorporate dampers, flexible joints, and tuned mass systems to manage these motions. Gravity provides the stabilizing weight that counters overturning forces. Elevated structures rely on gravitational load paths. Steel and concrete transfer compressive forces downward through columns and cores. Foundations spread these forces into the ground. If load distribution is uneven, stress concentrations can develop. Engineering calculations ensure that gravitational forces are balanced across structural elements. Even subtle variations in gravitational acceleration at different altitudes affect satellite fuel usage. A satellite in slightly lower orbit experiences stronger gravitational pull and more atmospheric drag. Over time, small corrections are required to maintain altitude. Orbital maintenance is a continuous negotiation with gravity. Telecommunications, weather forecasting, and financial systems all depend on satellites that operate within this gravitational framework. Signals transmitted from orbit to Earth cross tens of thousands of kilometers in fractions of a second. Their precision relies on stable orbits and corrected clock rates. What makes these systems remarkable is that gravitational effects are not theoretical curiosities. They are operational parameters. Engineers incorporate gravitational time dilation and orbital perturbations into software and hardware. Daily navigation, from aviation to smartphone mapping, depends on these adjustments. In daily life, gravity appears simple. Objects fall, structures stand, rain descends. Yet behind navigation systems, space traffic management, and skyline engineering lies a network of calculations grounded in gravitational physics. The same force that draws a stone to Earth also shapes satellite timing and structural stability. Through precise measurement and modeling, gravity becomes both predictable and indispensable. It anchors buildings, guides spacecraft, and synchronizes clocks. Quietly, continuously, it integrates the ordinary and the technological into a single field of influence. Gravity explains falling rain, planetary motion, and the structure of galaxies. Yet when astronomers began measuring how galaxies rotate, something did not align with expectation. The discrepancy was quiet at first, hidden in data points that refused to taper the way equations predicted. In a simple gravitational model, stars farther from the center of a galaxy should orbit more slowly. The reasoning follows from the inverse square law. As distance from the central mass increases, gravitational pull weakens. Much like planets in our solar system, outer stars should take longer to complete each rotation and move at reduced speeds. But observations revealed something different. When astronomers plotted galaxy rotation curves, meaning graphs that show orbital velocity versus distance from the galactic center, the lines did not decline. Instead, they flattened. Stars far from the luminous core moved at nearly the same speed as those closer in. This pattern implied that visible matter, meaning stars, gas, and dust that emit or reflect light, was insufficient to account for the gravitational pull holding galaxies together. If only the observable mass were present, the outer regions would not rotate so quickly without flying apart. The gravitational field appeared stronger than expected. In the 1970s, Vera Rubin conducted detailed measurements of rotation curves in spiral galaxies. Using sensitive spectrographic instruments, she examined the Doppler shifts of starlight to determine how fast stars were moving. Her data consistently showed flat rotation curves extending far beyond the bright central regions. These results were not isolated anomalies. They repeated across many galaxies. The implication was consistent. There must be additional mass contributing to gravitational attraction, mass that does not emit detectable light. This unseen component became known as dark matter. Dark matter does not interact with electromagnetic radiation in the way ordinary matter does. It neither shines nor absorbs light in observable ways. Its presence is inferred through gravitational effects. Galaxies behave as if embedded within massive halos, extending well beyond their visible edges. The concept reshaped cosmology. Instead of galaxies being composed primarily of luminous stars and gas, they are now understood to reside within vast dark matter halos. These halos dominate the total mass budget. In many galaxies, dark matter outweighs visible matter by a factor of 5 or more. Further evidence for dark matter emerged from gravitational lensing, meaning the bending of light from distant objects by intervening mass. When light from a background galaxy passes near a massive cluster, it can be distorted into arcs or multiple images. The degree of bending often exceeds what visible matter alone can explain. The additional curvature suggests extra mass. Clusters of galaxies provide particularly strong cases. The motion of galaxies within clusters indicates gravitational binding stronger than expected from luminous material. Without additional unseen mass, clusters would disperse. Instead, they remain gravitationally cohesive over billions of years. Dark matter also plays a role in cosmic structure formation. In simulations of the early universe, small fluctuations in density grow over time under gravitational attraction. Dark matter, interacting primarily through gravity, collapses into clumps that act as scaffolding for visible matter. Galaxies form within these gravitational wells. Despite its inferred abundance, dark matter has not been directly detected through laboratory experiments. Numerous detectors have been designed to observe potential interactions between dark matter particles and ordinary matter. So far, results remain inconclusive. The identity of dark matter remains unknown. Several candidate particles have been proposed. Weakly interacting massive particles, or WIMPs, are one possibility. Axions, hypothetical lightweight particles, are another. Each model attempts to reconcile astrophysical evidence with particle physics frameworks. None has yet been confirmed. Alternative theories have also been explored. Some physicists have proposed modifications to gravitational laws at very low accelerations to account for flat rotation curves without invoking unseen matter. These modified gravity theories attempt to adjust equations rather than introduce new mass components. However, many observations still favor the dark matter interpretation. The strength of the dark matter hypothesis lies in its consistency across scales. It explains galaxy rotation curves, cluster dynamics, gravitational lensing, and large-scale structure patterns in cosmic background radiation. The same unseen component appears necessary in multiple independent contexts. Yet its invisibility remains profound. Dark matter does not emit light. It does not reflect it. It reveals itself only through gravitational influence. Its distribution must be mapped indirectly, through motion and curvature, rather than direct observation. The work initiated by Vera Rubin transformed an unexpected measurement into a central pillar of modern cosmology. What began as a discrepancy in rotation speeds expanded into a new understanding of cosmic composition. The universe appears to contain far more unseen matter than visible stars. Gravity, once thought to be fully understood in terms of observable mass, now points toward hidden components. The motion of galaxies suggests that what we see is only part of the total structure. Beneath luminous spirals lies a deeper gravitational framework. In this sense, gravity acts as a detector of the invisible. By tracing how objects move, it reveals mass that cannot be seen. The flatness of rotation curves is not traumatic to the eye, but it carries immense implication. It suggests that the cosmos is structured by elements that remain beyond direct perception. The unanswered question is not whether gravity operates, but what exactly it is acting upon. Dark matter remains one of the most persistent mysteries in physics. Its presence is inferred, its effects measurable, yet its nature remains concealed. And through this concealment, gravity continues to guide inquiry toward deeper layers of the universe. If dark matter deepened the mystery of gravity, cosmic expansion widened it. In the early 20th century, observations revealed that distant galaxies are moving away from us. Their light shifts toward longer wavelengths, a phenomenon known as redshift. This shift indicates that space itself is expanding. Cosmic expansion does not resemble debris flying outward into empty space. It is the stretching of space between galaxies. On the largest scales, distances grow over time. Galaxies are not necessarily traveling through space away from a central point. Instead, the metric of space changes, increasing separation everywhere at once. For decades, it was assumed that gravity would gradually slow this expansion. Because gravity attracts mass, the mutual pull of galaxies should act as a cosmic brake. The question was whether expansion would eventually halt, reverse, or continue forever at a decreasing rate. In the late 20th century, observations of distant supernovae suggested something unexpected. The expansion of the universe is not slowing, it is accelerating. Galaxies are receding from one another at an increasing rate. This acceleration implies the presence of a component that counteracts gravitational attraction on cosmic scales. This unknown influence is called dark energy. Unlike dark matter, which contributes additional gravitational pull, dark energy appears to drive space apart. It does not clump into structures. It behaves as a property of space itself, exerting negative pressure, meaning a form of energy that causes expansion to accelerate rather than decelerate. Dark energy is not observed directly. Its presence is inferred from the behavior of large-scale cosmic expansion. Measurements of supernova brightness, cosmic microwave background radiation, and galaxy clustering all converge on the conclusion that a dominant fraction of the universe consists of this expansive component. Current cosmological understanding is often summarized in the lambda CDM model. Lambda refers to the cosmological constant, a term representing dark energy as a constant energy density filling space. CDM stands for cold dark matter, meaning dark matter composed of slow-moving particles that interact primarily through gravity. In this framework, the universe consists of roughly 5% ordinary matter, about 27% dark matter, and approximately 68% dark energy. Gravity governs the interaction between these components, but the behavior of dark energy introduces repulsive effects on the largest scales. The cosmological constant was originally introduced as a mathematical possibility. Its physical interpretation remains uncertain. It may represent vacuum energy, meaning energy inherent to empty space itself. Quantum field theory predicts vacuum fluctuations, but the predicted magnitude differs dramatically from observed values, creating a profound theoretical tension. While dark energy operates across cosmic distances, another unresolved question lies at the opposite extreme: how gravity behaves at the smallest scales. General relativity describes gravity as curvature of spacetime, but quantum mechanics describes forces in terms of particle exchange and probabilistic fields. These frameworks remain mathematically incompatible. Physicists seek a quantum theory of gravity, a model that reconciles spacetime curvature with quantum principles. In quantum field theories of other forces, interactions are mediated by particles. By analogy, gravity might be carried by a hypothetical particle called the graviton, a massless spin-2 boson that would transmit gravitational interaction. The graviton has not been detected. Its existence remains theoretical. If gravity is indeed mediated by such particles, they would interact extremely weakly, making direct observation extraordinarily difficult. Yet incorporating gravitons into a consistent quantum framework remains a goal of theoretical physics. Alternative approaches attempt to quantize spacetime itself. Some models propose that spacetime has discrete structure at extremely small scales, rather than being continuous. Others explore string theory, in which fundamental particles arise from vibrational modes of extended objects. In several of these models, gravitational behavior emerges naturally. The challenge lies in testing these ideas. Quantum gravitational effects are expected to become significant at the Planck scale, distances and energies far beyond current experimental reach. Observational windows may come indirectly through black hole physics, early universe cosmology, or subtle imprints in gravitational waves. Dark energy and quantum gravity represent opposite ends of the same question. At vast scales, gravity appears to weaken relative to expansion. At microscopic scales, its integration with quantum mechanics remains incomplete. The force that once unified falling objects in planetary motion now opens questions that stretch across all scales. In this context, the earlier work of Vera Rubin carries quiet resonance. Her observations revealed that visible matter was insufficient to explain galactic motion. The universe contained more than met the eye. Today, dark energy suggests that even gravitational attraction itself does not tell the full story of cosmic evolution. The arc from falling apples to accelerating galaxies reflects expanding understanding. Gravity has moved from intuitive downward pull to geometric curvature, from planetary architecture to unseen mass and expansive energy. Each layer solved earlier puzzles while revealing deeper ones. Yet uncertainty does not diminish coherence. Observations align consistently within current models. Galaxies cluster as predicted. Cosmic background radiation matches calculated patterns. Expansion accelerates at measured rates. The structure holds, even as its components remain partly concealed. Gravity remains the connecting structure across every scale we have explored. It governs the motion of galaxies, responds to unseen mass, and exists within a universe whose expansion accelerates over time. What once appeared to be a complete description of attraction now sits inside a broader cosmological model that includes dark matter shaping, structure, and dark energy influencing expansion. The equations remain powerful, yet the contents of the universe they describe are only partly visible. From the descent of rain through the atmosphere to the recession of galaxies across billions of light years, gravity provides continuity. It organizes matter into stars, holds planets in orbit, defines the rhythm of tides, and reveals hidden mass through motion. Even where it appears weakest, on cosmic scales stretched by expansion, it still determines how structures form and persist. Across daily life and distant space alike, gravity does not disappear. It bends light, guides satellites, shapes bone density, and anchors buildings to the ground. Its story is not one of completion, but refinement. Each answer has widened the field of inquiry, leaving us with a force that is measurable, dependable, and still not fully understood, quietly structuring a universe that continues to evolve.